start recording and now let's continue with this. Okay, you might have my screen now.
Yeah, we can see it now.
Okay. Here you saw that I defined two perspectives for solving some problems. For example, when our problem is that what is velocity in this pipeline, it does not give sense. As an engineer, you should ask me, okay, velocity where or velocity of which water molecule, okay? If I if I ask you velocity of this water molecule, you can say that, okay, here the velocity is something, then here is another thing. Here the velocity varies because there is a bend. Here there is a change in the diameter. Again, you see the molecule moves at different locations. And therefore, if you want to answer me when you consider the molecule location, or when you monitor molecule by one molecule by time, it is called the Lagrangian point of view. And it is really difficult, yes. Instead of that, I can say, okay, no, I don't mean to find the velocity of this specific molecule. I'm just asking you, tell me what is the velocity of water here at the outlet, because this is very important to me to know the water velocity here, or velocity at this section, at the this bend. So this is called Eulerian perspective. In this course, we will continue Eulerian perspective. And this is more simple. You see, it is more convenient than a Lagrangian perspective. To solve such a problem, we always need to define our control volume, as you saw here. For example, in Eulerian or Lagrangian problem, we have control volume. Then we consider inflow, outflow to the control volume. Then we use principal rules of physics like Newtonian, first or second or third law of Newton, or conservation of mass, conservation of momentum, and these rules will help us to find the answer. For example, what is the velocity? And your duty actually is this. In this course, you will learn how to calculate velocity in a pipeline. At the same time, pressure and other features or discharge in a pipeline system. This is our aim. So here I can summarize that the control volume technique is useful when we are interested in the overall feature of a flow, such as mass flow rate. Mass flow rate, you remember in hydrology, I talk about mass flow rate is called flux, yeah? Mass flow rate is called flux. Mass flow rate into and out of the control volume, or net forces applied to the bodies. Differential analysis, on the other hand, involves application of differential equations of fluid motion to any and every point in the flow field over a region called the flow domain, okay? And when solved, these differential equations yield detail about the velocity, density, pressure, etc. at every point throughout the entire flow domain. Okay, we accept this. Lagrangian perspective is difficult, but provides more details about flow at entire domain, at every point of control volume, but Lagrangian, but Eulerian gives us one solution for the entire control volume. If you want more detailed solution, you should take several control volumes. More details you will understand during this course. Again, this is the definition of control volume. A suitable mass of fluid can be identified by using control volume. Sorry. I don't see both are. A suitable mass fluid can be identified by using control volume. A control volume is a purely imaginary region within a body of flowing fluid. The region is usually at a fixed location and of fixed size. Inside the region, all the dynamic forces cancel each other at the inside. Attention may therefore be focused on the forces acting externally on the control volume. For example, my aim is to find velocity in here. What's the velocity here? I select such a control volume, and then I can say that water, for example, enters from here, goes out from here. What are the forces at this input area? It is called control surface, okay, surface area. And what is the force acting output area? Then using the main principles of physics, we can find velocity here. The other concept that we should know is 1, 2, and 3-dimensional flow analysis. In this course, we analyze our problems one-dimensional. What does it mean? One-dimensional flow requires only one coordinate to describe the change in flow properties. Two-dimensional needs 2 coordinates and 3-dimensional 3 coordinates. What does it mean? Let's show you in that way. For example, when I assume that water moves in this direction, comes this pipe and goes out from here. Okay, this is output, this is input. If I ask you what is the velocity, you can ask me, okay, velocity at which direction? Because velocity is a vector. It means that you can have these kind of systems, for example, x, a coordinate system, y and z, okay? Okay, so if I consider only velocity at flow direction, you see what is my flow direction? Flow direction is x. Here my flow moves at x direction. Therefore, one direction, you consider one direction, and what you give me is v at x direction. Let's say Vx equals to, for example, 1 meter per second. This means that in this section, you find velocity, just velocity at this direction. Actually, if you look to the section, this is something like this, yeah? A circle full of water. You see different layers, okay? This is let me draw it in red color. Okay, this what? Sorry, pain. This is my y direction, yes? Sorry, z direction. Z direction based on this coordinate system, I have also this, it could be x or y. What's your idea? It is y or x? It is y direction, as you see here, y direction. This is y direction, and we can show this like this. Here y, this is x, and this is z. And you see here, so you gave only Vx, which is perpendicular to you, okay? What comes to you in this section. However, water velocity can vary also at this direction. You know that maximum water velocity is at the middle, because at the wall, the velocity is always 0, non-slipping condition, you remember? Therefore, at this direction or y direction, at z direction, water varies. But you neglect them. You just gave me Vx as one direction, at this direction, okay, at this x direction. And which is the average velocity at this direction, and this is called one-dimensional. If you give both, if you find V at x direction and also at y direction, it is called two-dimensional. If you consider 3 of those coordinates, this is called three-dimensional. And at last, we are talking about fundamentals of law of physics that we will apply them on control volume to solve our problems. The fundamental equations are conservation of mass, conservation of energy, and conservation of momentums. Conservation of mass can be neither created nor destroyed. We already in hydrology said this is called water balance, yes? Do you remember water balance, conservation of mass? Or Jeren told this is the same with continuity equation. And conservation of energy is energy can be neither created nor destroyed. Conservation of momentum, a body in motion cannot gain or lose momentum unless some external force is applied. Do you remember what was the definition of momentum? Yeah, about continuity of equation I talked. And momentum is mass times velocity. Mass times velocity is momentum. Okay, by this presentation, we completed our chapter 1. And I don't want to start chapter 2 today, because actually I'm not satisfied with you, with all of you, because you never contribute in the course. You never ask a question, and unfortunately never answer, unless I push you to answer. I know that you know some answers. Anyway, in order to be more communicative, more active in class, I would like to ask you to study one chapter before that teaching, okay? Your book, your textbook is in your hand. And for next week, I will start chapter 2, hydrostatics. Okay, go, please study the chapter yourself first. Definitely you will learn something. It will help you to communicate in the course. And also you will have some questions. Again, you have in the course, you can ask some questions. It is another contribution. Therefore, from next week, I suppose that all the students already studied at least 4 or 5 pages of the chapter, maybe which I'm going to cover it. For next session, I will talk about point pressure, manometers. Okay, the topic is hydrostatic. I will talk about manometers and calculation of pressure at point. So get ready for that chapter, and I hope you contribute. You 3 students also, Emre, Malike, and Makbule. Thank you for your attendance. Do you have any question? Okay, next time you promise me that you will have some questions and you will contribute more, okay? I'm really waiting for your contribution. Okay, thank you so much for being in this session, and see you at next session. Bye-bye.
See you, Hocam. Have a good day.
Thank you. Bye.
See you, John.
Thanks.